and I want to welcome you to the second CESSRST seminar of the spring semester. Try saying that 5 times fast. It's a good thing I'm not Sylvester the cat, otherwise it'd be saliva all over my screen here. I think you all know in the fall was the very first semester of the CESSRST seminar series, and it went very well. This spring, we really have quite a lineup for all of you. We have some of our speakers this spring are legends in their field. So you are all in for a treat this spring. You're going to be able to watch some, attend some very exciting talks. Mark 12:30 every other Thursday on your calendars. We will deviate from that schedule in April, but there will be announcements on the CESSRST website. And of course, you'll get emails. And if you want to see when all of the CESSRST seminars are right now, you can go to the CESSRST calendar. Just go to cessrst.org, go to news and events, then click on just plain events, and that brings up the calendar. Now today we have a special seminar in that we have Hernan Moreno, who will be speaking to us, and he is a new professor at UTEP, University of Texas, El Paso, and which, as many of you know, is a CESSRST campus. So today we get to welcome Dr. Moreno to the CESSRST family. Now I asked Hernan if I could say a few words to the students before he gets going here, and he very graciously said yes. So I just want to take a few minutes to talk to our CESSRST students who we ask to attend all of these seminars. And I want to talk to them because I know a lot of them are probably wondering, why should I attend a seminar that has nothing to do with the topic that I'm researching? For example, you might be doing research on hurricanes and there's a talk on urban pollution, and you may say, how do I benefit from attending that seminar? And the answer is there are numerous ways that you will benefit in a big way. First of all, you don't want to be a one-trick pony as a researcher. You don't want to have tunnel vision and just focus, just study in one topic. You want to broaden your horizons. You'll feel like a more complete scientist if you are familiar with many topics. And you'll have a better understanding of the topic you're most interested in if you see how it fits into the big picture. Also, if you become a scientist or a professor and you're researching your favorite topic and you focus on that, and then the funding gets tight for that topic, then you're out of luck. You know, if you're not familiar with anything else, you're not going to be able to branch out and do research in other things if the funding dries up in your area, which is why many colleges and labs will not want to hire you if you just know one thing. They want someone who's flexible and who can branch out on other topics if needed. So attending these seminars will help you broaden your horizons and keep you from limiting yourself as a scientist and keep you from limiting your career. Okay, so secondly, you might be asked to attend a seminar, or you are asked to attend these seminars, and maybe one of them looks like it has nothing to do with your research, but in fact it might. You might be surprised. I know this firsthand because when I was doing the research for my dissertation, I was studying hurricanes. I had no intention of investigating aerosols, but I attended a seminar that taught me that aerosols and aerosol concentrations could have a big effect on hurricane formation and intensity. And I wound up incorporating aerosols into my research, and the relationship between aerosols and hurricane formation became the focus of my dissertation. So you might be surprised that some of these topics that appear to not be related to your work really are. And even if they're not now, maybe someday down the road, someone will discover that there is a physical connection between the speaker's topic and your topic. And you'll say, gee, I wish I knew more about that topic. And just related to all of this, your interests may change down the road. Maybe someday down the road, you find yourself gravitating to another topic and you'll say, gee, I wish I knew more about that, but you find it hard to get into that because you're not too familiar with it. So your interest can change. Lastly, final thing here, when you attend these seminars, it's very likely you will pick up some logistical information that will be of use to you. For example, you may learn about a satellite instrument that you weren't familiar with that has data products that you can use for your research. Or you might learn about some other type of data set that you can use. You might learn about a computer model that you can use for your research. Or you might learn about a statistical technique that you were not familiar with before that you can use to do investigations that are related, that will benefit your research. So it's very likely you'll pick up some, that happens all the time. It's very likely you'll pick up some information of general use that you can use for your particular research. So there you go, 3 reasons. And there's other reasons. I just don't have time to get into them. And just very quickly, many of these topics that these speakers will present results that are really cool and fascinating. So you'll just enjoy the talk. But anyway, many reasons to attend these seminars. So treat them like a class. Pretend there's going to be a test at the end and pay close attention to these talks, even though they may not be related to your favorite topic. And I would suggest having a pencil and a piece of paper handy in case there is something of interest to you or something you want more information about. Okay, so that's my little pep talk to the students. Now, our speaker, as I said, is Hernan Moreno. The title of his talk is Merging Multi-Platform Sensors, Models, and Artificial Intelligence for Advanced Hydraulic Prediction. So right there, that sounds pretty cool. Dr. Moreno got his PhD from Arizona State. He went on to hold 2 postdocs, one at Arizona State and one at the University of Wyoming. He earned an early career award from the Army Research Office, and now he is an assistant professor in the Department of Environmental and Resource Sciences at UTEP/CESSRST. So with that, I'll hand it over to Hernan. Hernan, go ahead and take it away.
Thank you, Chris, for the nice introduction. And I also support you in your messages to the students in terms of learning, regardless of who's speaking, learning about skills, learning about tools, learning about objectives and stuff like that. It's all about learning in the end. So let me go ahead and share my screen to all of you. If I can share it. Okay, can you see my screen now?
Yes, I can.
Okay, excellent. All right, so I'm gonna go ahead and get started, and we're gonna leave questions for the end. My presentation, Chris, I guess is gonna be around 40 minutes or something like that, so I don't get bored your students or other researchers. Is that good? Is that okay?
That sounds perfect.
Okay, so what I'm gonna talk about today is merging multi-platform sensors and models with some tools of artificial intelligence or machine learning for advancing hydrologic understanding and prediction. And this is kind of a compilation of my career for the last 10 years. So I'm sorry if I don't provide a lot of details on some of the tools and methods that I used, but what I wanted was good for this seminar is to give you a broad overview of what I do, so you can do more research in the future for specific areas if you consider to do so. So the areas of the main questions, the processes that drive our current climate and hydrologic world or some of those are written here on the left: climate variability and change, extreme events, aging infrastructure, population growth, and land cover change. So every day we get pretty much one news about climate change, aging infrastructure here in Texas, extreme drought in California, population growth in the world, land cover change everywhere. Um, but we also, as scientists, we have different tools. Like one of those tools is field observations, um, remote sensing, very important. Machine learning tools are the new statistical tools for doing research. We also have distributed modeling, and in all of that, we have decision-making platforms that kind of um, put all these spheres together to try to make the best decisions for our future. In the middle, like, is what I study, hydrology and water resources, but in the end is society, what we try to benefit. The outline of my presentation, again, is this one over here. I would like to provide some overview of some extreme events, hydrology and flooding, and some research I've done using some remote sensing products. Um, I also would like to talk about some processes occurring after wildfires or post-fire hydrologic processes. Number three, I want to talk about water scarcity and sustainability. Um, and these apply to the Oklahoma, Texas area. Number four, I would like to predict or to talk about predicting energy fluxes at engaged locations. And finally, I would like to talk about evapotranspiration for partitioning. As you could notice from this agenda, some of the topics are fundamental topics in hydrologic science, but some of them are more applied. As faculty, we usually have to combine both of them to get, the best sources of funding for our research. Um, so let's begin with extreme event hydrology and flooding. So here, the main message what I wanted to talk about is the fact that um, uh, uh, there have been in the United States and in the world in general a lot of catastrophic events related to heavy precipitation. And for example, this is an animated loop of water vapor systems over the North American continent. This was in September of 2013. This is shown by GOES 13 and GOES 15. There was a cold front coming all the way from the North Pole, and then that cold front gets stuck over here, the Rocky Mountains. They became stationary and produced a lot of rainfall. The problem with the Rocky Mountains is that this is a very topographically complex area. So small size creeks and watersheds in the area, like the Thompson or the Boulder Creek, they became huge, and they did a lot of erosion and they produced a lot of economical damages downstream. So this is a map showing a 3D on the left, a 3D view of the flooded area that was caused by a 500-year return period storm. um, so there's still many questions about these events, and one of the questions. Let me jump into this slide. One of the questions is up to what degree the new tools and the new remote sensing um, methods and radiometric capacity of the radars can help us improve our forecasting skill. So this is part of a work that I did during my PhD in Arizona State University. I was invited by the National Center of Atmospheric Research, NCAR, to stay at the main headquarters in Boulder, Colorado, where we used different nowcasting models, and then the one that I ended up using because of its accuracy was the Titan model. Um, and that Titan model that uses an extrapolation technique to predict the motion of clouds and the velocity of the clouds and the rainfall, was used to feed a distributed hydrologic model. This is an example of the model at one of the watersheds, and the model is fully distributed. It's a resolution of 30 meters. So I put a lot of predictions of thunderstorms into the model for different lead times. Lead time is the prediction time in the future. And our main questions were to basically know what happens in terms of the uncertainty of forecasts with lead time or the time of prediction. So we did this both at the rainfall level and then also at the hydrologic level to see if these functions replicated or propagated into our models. So we did the simulations at 11 watersheds, all of them ranging from 0.1 square kilometers to 350, to be able to identify those patterns in predictability. So the model that we used is the TRIPS. TRIPS model was developed in the 1990s in MIT. This is a fully distributed physics-based model. The model represents very well the vegetation, terrain, soils, the vadose zone, the saturated zone, and everything inside a watershed. So it requires a lot of information, and a lot of this information comes from remote sensing sources and radar sources. For example, the DEM was derived from the shuttle SRTM product in USGS. The land cover types were derived from the NLCD, NASA National Land Cover Data Set at 30-meter resolution. Uh, and we'll talk about other inputs from remote sensing, including precipitation and temperature and clouds. For now, let's talk about the model. So the model is pretty comprehensive. It basically replicates all the processes of the hydrologic cycle, including interception, evapotranspiration, infiltration, overland flow, stream flow. It also accounts for interactions from, between the beta zone, the saturated zone, and the surface. So it's pretty comprehensive, and it doesn't only account for the water balance, but it also accounts for the energy balance. Yeah, and it also includes snow processes in when temperatures go below 0 degrees Celsius. So let's jump into the results. The test basins, they were all in the Colorado Front Range area. So the Colorado Front Range is right here. As you could see, these were the watersheds that I used in my simulations. A lot of them were influenced by snow, but some of them uh, did not have snow since it was basically summer convection storms that I decided to simulate. There were 3 radar systems nearby the area that you could see here over this image. And there were multiple rain gauges and stream flow gauges in the area that I used for basically calibration and validation of the model. So here, this is a level 2 radar image animation showing the type of storms that happen in summer in this area. As you could observe, those are very localized. And basically it's local convection, heavy convection systems that form cumulonimbus clouds that create a lot of intense precipitation. So um, so we decided to take some of these storms to make simulations and see how if the model was able to reproduce what was happening in the terrain. And if you can remember from your classes in your hydrology classes, one of the main problems of the models, hydrologic models that we have in engineering and science, is that they're not able to capture very well the internal variability of the watersheds. So in other words, the rational method, for example, or the soil conservation service method, or the unit hydrograph method, none of those methods are able to, number one, characterize um, distribution of rainfall or runoff inside the watershed, and number two, it doesn't they don't do not account for heterogeneity of vegetation or changes in vegetation or terrain inside the watershed. Those are pretty much very static, very first order models that engineers use. But in the end, science and engineering is going to have to move in the future to models like this, because of the flexibility of the physics based approach, and because it basically accounts for a lot of the variables and changes within the watershed, including those changes induced by climate change and land cover change. So as you could see here on the top, you could see how the different products of remote sensing or radar based product like level 2 1 kilometer resolution, level 2 4 kilometer resolution result in different um, production runoff production um, patterns. But foremost, the hydrologic model is able to reproduce where runoff is occurring. And so when you observe the hydrograph at different points along the channel, you're correctly simulating what happens, right? So for example, point A here observes very little response to this rainfall event. But then point D here observes a little bit more, right? Because the water has been accumulated. But it depends where water occurs, where precipitation occurs, that different nested subwatersheds observe stream flow responses. So this is one of the benefits of using a distributed hydrologic model for distributed rainfall information. And with the advance of the remote sensing area and global precipitation measurements, these models become more relevant because now we have to fully utilize the power of having distributed information. Okay, and this is one way using distributed models, not only in hydrology but also in environmental science in general, or earth science in general. So in the end, we end up, one of the conclusions was that since forecasting skill is not better than 30-minute lead time in radar products, our watershed models were also not better at accurately forecasting stream flow beyond 30-minute lead time. Which means basically you're tied to the accuracy of the remote sensing data. And most and most accurately, you're basically leaning on the accuracy of the models that are based on radar precipitation to determine the accuracy of the hydrologic models. Let's now move forward toward another area of research, very exciting area, that deals with hydrology after wildfires. And so, in a drier world, in a world that is becoming warmer, really, we have to be more prepared to deal with fires. This is something that we're going to encounter more and more frequently, not only in the United States, but in the world in general. The world is becoming warmer. That's a substantial, clear, concise, and a very, very evident trend in the world. And one of those consequences of the world being warmer is that there's more potential for wildfires to be induced, to start. And so this map on the left shows the red polygon showed where wildfires have occurred in the Western United States during year 2008 to years 2017. As you could observe, California is one of those areas that have observed a lot of forest fires, but also the entire Midwest and Southwest area had a lot of wildfires. Um, so the problem is, after the wildfires themselves is a problem, but after the wildfires, when the precipitation season begins, then the watersheds respond very efficiently to any precipitation event, even though if the precipitation event is low. So we had numerous reports of flooding, flash flooding, and landslides occurring after the wildfires. So we thought this could be a cool contribution to science if we could perhaps study the how remote sensing can help us understand the changes induced by wildfires in terms of the hydrologic modifications, and how can these tools help us predict where those big flood events will occur. So we went ahead and took an example, the Waldo Canyon fire that happened in June 23rd through July 10 in 2012 here in Colorado Springs in Colorado. This is the area that got burned, a lot of acres burned, and you can see here a neighborhood photo and how close this fire occurred. Okay, on the right you see one of the watersheds that got affected by the fire. It's called the Camp Creek watershed. So I went ahead and did this polygon. This polygon hatch here is the area that got burned. So luckily I had data before the fire and after the fire, so we could compare how the two responses um, uh, changed. I mean, the one pre-fire and the one post-fire. And here's what we did. By the way, this is a photo of a volunteer looking at the disaster occurred right after that fire in 2013 in Manitoba Springs, Colorado. A lot of damages and life losses. But one of the things we wanted to do is to compare two time series, the time series of the um, a stream flow response pre-fire, after pre-fire and after fire. Okay, and on top you have the precipitation. So precipitation in bars. This is I think this is daily precipitation, and of course after there's an event that it's um, higher than any of those events that happened 6 years before. But anyhow, the rest of them besides this look like very similar to the precipitation events before the fire. The fire occurred here in this uh, red window, and as you could see, the stream flows changed dramatically after fire. Okay, so we went ahead and downloaded some images from MODIS satellite and try to compare what happened to MODIS before fire and after fire. Okay, so we went ahead and downloaded the normalized burn ratio from MODIS. We calculated ourselves from MODIS. Okay, the normalized burn ratio compares some bands in the red and infrared parts of the spectrum. And what we did is we observed, the variability of the NBR pre-fire, and then post-fire, this is what we observed. The green lines or the green dots are now how it behaved. So the NBR changed dramatically pre-fire to post-fire, okay? So these orange dots really represent what happened in another watershed that was not affected by fire. So basically, the remote sensing information is telling you that something very, very hard, very, very strong happened in the ground. And we try to link those remote sensing indices in terms of our common hydrologic knowledge of the hydrologic response in terms of the peak flow, the effective flow, and the base flows, right? So the first thing is that the runoff coefficient, which is the ratio of the effective flow or the effective runoff divided by the total precipitation, changed. So it changed dramatically in two orders of magnitude across different storms of all the sizes. Okay, so that's one conclusion. Conclusion number two, the peak flows or the maximum flows, they increase in one order of magnitude across all storms that we selected. Remember, we selected 4 east storms before fire and 4 east storms after fire. And the size of the storms are shown here. Okay, this is the total cumulative precipitation for each of the storms. So yes, the watersheds changed dramatically after fire, but we wanted to investigate how the remote sensing index could help us kind of predict or advance our knowledge in how big those changes are in terms of hydrology. So the delta NBR is the difference between NBR pre and post fire. So we went ahead and calculated the delta NBR for each of the seasons, each of the years in which those, the fire year in 2012 and pre-fire. All of the years pre-fire pretty much showed that the NBR was slow, although some of the years were wet and had high runoff coefficients. We could conclude that these years were El Nino years, where they have anomalous precipitation. Precipitation where was very, very high and snow was very high. But in the other years that were not El Nino or had anomalous amounts of snow, pretty much all of the years behaved like an anomalous precipitation season, right? All of them have higher than normal runoff coefficients. And so we did all of this to year 2017, expecting to have a hysteresis effect that closes down all the way to normal conditions. However, the fire was in 2012, and up to 2017, the watershed was not fully recovered. And we expect it takes at least another 5 years more to get back to normal. Okay. Now here, this is one of the places where we used machine learning tools to be able to recognize the importance of variables. So this is one of the tools we used. It's called the best subsets. Best subsets is a future elicitation machine learning tool that help us identify the variables that contribute the most to the variability of a predictant. So here on top you have, we isolated all the pre-fire events, the 40 pre-fire events here on top, and the 40 post-fire events here at the bottom, okay? So in all the pre-fire events, the variables that were most important were the total precipitation of the event, the average intensity of the event, and the maximum intensity of the event. In one of the cases, delta NVR was important, but we believe it was due to the phenologic changes in vegetation, not the fire, of course, because pre-fire, there were not fires in the area. However, if you look at the post-fire events, all of them had strong influence by the change in land cover, except by the change in the response time of the watershed. That doesn't seem to be affected at all by the change in land cover. But this is an important message. You have to have into account the change in land cover in all the hydrologic models you're doing after a fire had occurred in a watershed. It is as important as having correctly estimated the rainfall. Okay, that is lesson or bottom line of this study. Now, moving on to water scarcity and sustainability. This is an important question. We were motivated by the fact that in the United States, during the last 20 years, there has been an observed trend in temperature change towards warmer temperatures. In general, there have been some small areas of a cooling trend, but in general, the United States going to warmer temperatures. Those changes in temperatures, of course, trigger changes in the energy budget, changes in cloudiness, changes in lifting processes for air parcels. So that leads to changes in precipitation also. So this is the map showing the changes in precipitation that are observed between 1991 and 2012. So in most areas, precipitation is increasing by far, like around 10 to 15%. But in some other areas, like the southwestern United States, precipitation is not changing much. In fact, it's actually decreasing. But one of the watersheds we wanted to study is this one that is in the boundary between drier and wetter conditions, the River Basin here in the border between Texas and Oklahoma. This watershed had observed the most ridiculous changes from, very severe droughts in 2014. This is Lake Texoma in 2014, almost almost dried out by the um, intense drought that occurred in March 2014. But also the next year in 2015, this is what happened to the same lake. Uh, you know, incredible amounts of rainfall and snow melt produce these flooding over the same Lake Texoma in 2015. So we have to get accustomed to these type of extremes with climate change. Uh, very, very intense, more frequent droughts, and very, very, very intense, more frequent floods. We have to combine climate change with some other changes that are occurring here on the ground. For example, one of them is land cover change, and for economical reasons, number one, but also for to reduce the risk of fire, and in general to increase the area that is inhabited by humans and not by nature. So one of those projects in the United States is the Forest Restoration Initiative. So this is part of a federal initiative that is aiming to reduce forest cover in different areas of the United States where the risk of fire is high. And these projects are occurring in the Mogollon Rim in Arizona, and the Sierra Nevada mountains in California, but also the Rocky Mountains in Colorado. And basically what the projects are trying to do is to reduce the normal density of trees to less fractions like those shown here in this polygon. Okay, so by having less trees, the argument is that number one, the fire fuel will be less, so there will be less prone to propagate a fire. And number two, there will be economical revenues for the regions that will have more wood supply to bolster the economy of those municipalities. Now, the question is, when you reduce forest from historical high levels to um, virtually half of what they were, we should expect a hydrologic consequence. We don't know what consequence that was, so we decided to went ahead and try our hydrologic model into these areas where the forest restoration was occurring. This is what the model is very comprehensive. It basically accounts for the continuity equations everywhere, from the surface, the snow, to the vadose zone, to the groundwater area. Basically accounts for evapotranspiration and the partitioning of evapotranspiration and different runoff types, including overland flow, saturation excess, perch, groundwater contribution, etc., etc. So all of those, we went ahead and tried our hypothesis here at the Tonto Creek Basin in Arizona that was being themed. And what you observe here on the left is a map of forest cover, basal area, and pretreatment, and the projections that they are going to end up with. The reductions of up to minus 225 feet square per acre. Basically, what looks like this will look like this. It's occurring right now and will happen in the future. So this is the information that we use for our modeling project. We went ahead and collected data from snow till stations, stream flow stations of the USGS. We went ahead and did some field trips and took some measurements in the area. We also collected data from vegetation from the USGS National Land Cover Dataset at 30-meter resolution, but also soils from the Surgo and Statsco database, and bedrock depth from the USGS. We put this into a model and we run the model, calibrate it versus stream flow, but also snow water equivalent. By calibrating this, and see, this is one good important message for students. When you calibrate a model, make sure you calibrate it with different targets so you avoid equifinality problems. Equifinality problems are basically type of problems that you get when you only have one variable to calibrate. The problem is that you could have calibrated the model, you could have different parameterizations to resolve the same problem. Okay, so basically you're not getting the right answers by the right reasons for the right reasons. You're getting the right answers for the wrong reasons, because when you have different different variables, target variables to calibrate, you're basically reducing the universe of potential solutions of your problem. So the more variables you have, the more information you have to calibrate your model, the better. Okay. Now these are some of the projections that we obtained with this calibrated model. Number one, at the top of the basin, here at the forest thinning area, the runoff changed so much and changed positively, meaning that these areas effectively produce more runoff for the same amount of precipitation. For the soil moisture, though, we didn't observe dramatic changes in one or another direction. We see mixed changes, same as for evapotranspiration. But the most dramatic changes occurred in snow. Okay, so we had here two variables to measure snow. One was the longest number of days with continuous snow cover, and the number two was maximum season snow water equivalent. So for the two of them changed negatively, meaning that these areas that produce snow, which by the way, snow is the main resource that provides water to 4 million inhabitants in Phoenix, Arizona. So snow, for the lack of trees and lack of vegetation, was melting faster than normal. And that change was up to minus 60 days in advance. So normally snow starts to melt in April 1st in Arizona. So 2 months before would mean February. So it means, without trees, the melting season would begin up to 2 months before in some of these pixels. Of course, the average is 1 month before. So March would mark the start of this melting season. And same thing we observed in the snow water equivalent. Snow water equivalent was heavily reduced from zero all the way to 100 millimeters, 200 millimeters, basically at 300 millimeters in some area, a third of a meter, which means this is very, very bad for our reservoirs downstream. Okay. Now, moving into another exercise, again in the Red River Basin, this is in the border between Oklahoma and Colorado. We wanted to investigate what we're going to go the effects of climate change on the water supply and water availability in this region. But we not only accounted for climate change, we also accounted for water use, because as important as climate change is um, um, the use of water, is the population attitude to use or consume water. So here is the Red River Basin. It has a number of dams and reservoirs depicted here with the black dots that you could observe. Um, so the watershed covers New Mexico, Texas, Oklahoma, Arkansas, and Louisiana. A population of 4.3 million live in this watershed. Climate gradient from semi-arid here in the top Texas Panhandle all the way to Louisiana to subhumid. And there is a high dependence on surface water in these reservoirs for survival. So we went ahead and took the general circulation models that were most accurate in the area. Of the 51 models, we end up selecting 3 of those models: the CCSM4, Miroc C5, MPI model. And we wanted to see what happens in terms of the runoff production, right? So basically the models, what they predict is a lot of uncertainty. So here's another lesson learned. Whenever you look at the climate models, they all convey uncertainty, but you have to be careful. You have to be careful to investigate what happens before you write your conclusions, okay? So here's the RCP, different representative concentration pathways, meaning the different concentrations of CO2 in the atmosphere, right? This would be like almost business as usual. And these will be higher concentrations of CO2 in the atmosphere that make the atmosphere warmer. So some of the models even predict more rainfall than normal in the east of the watershed. Okay, but here's the thing. We took all these general circulation model outputs and combined it with the use of water per county in these watersheds. And we actually calculated an index based on the water availability or the change in water availability on the numerator and the change in water demand in the denominator. We actually projected the water demands according to the current populations in these areas. And so this index actually tells us how much water it is available per county, basically, relative to the present, where number one means the current, the present values. Blue values mean more water than right now, and red values basically mean less water than right now. So when you combine all these general circulation models with the water projections, the water use projections, is when you obtain a clear message. That is when you observe that pretty much all of the models coincide in giving you the same conclusion. There are going to be some counties in high risk of being under supply of water, but there are some other counties that have oversupply of water, or the consumption of water is not as heavy as other counties. So by combining those two metrics, we could obtain conclusions that are more certain, more targeted. And number three, we can actually talk to decision makers now in terms of involving population into the projections and not only climate change. So this way, we all go in the same direction in showing what areas need um, um, you know, um, investments into water infrastructure or policies that make water supply better for the future. Okay. I think I'm only having around 5 to 6 minutes to wrap up my messages. I'm going to go ahead and jump into these new topics of predicting surface energy fluxes and soil temperature in engaged basins. This was a, um, research work funded by the Army Research Office. The other two were funded by the USGS and NOAA. So here, this is one of the questions that one of the most important equations in hydrology is the energy, radiation, carbon, and solar radiation balances. So here on the left, you have the hydrologic balance equation, but horizontally, you have the energy balance equation. Here in the down, you have in the bottom, you have the carbon balance equation. But here on the right, you have the solar radiation balance equation. All of them have some elements in common. For example, net radiation is very important, and it appears in three of the equations or four of the equations. And precipitation and latent heat flux is another one that is important that appears in two of those equations. By the way, latent heat flux is what we know as evapotranspiration. So with one of my recent students in University of Oklahoma, Jorge Celis, we wanted to investigate what happened in terms of um, getting more information and better information in areas that were not equipped with these type of uh, um, tools. In the screen you're seeing one eddy covariance tower, one micrometeorological tower that, in average, these towers can cost all the way from $40,000 to $100,000. You could put as many sensors as you want, but basically what these sensors do is they measure all the components of the energy budget, shortwave incoming radiation, downwards, long wave outgoing radiation, inwards and outwards. You could measure carbon fluxes, you could measure soil moisture at different depths. And of course, the regular, here in the left, you have a regular weather station. So our mission, the question that we had here was, can we use a land surface model, our hydrologic model, as a virtual tower so that we can convert a regular weather station that looks like this into one Erecovariance station, of course, for use in areas where installation of this tower is prohibiting, either because of the accessibility or because of the cost. So our answer was, okay, let's go ahead and see what we can obtain. So here is what the United States looks like in terms of the rain gauges for hourly measurements. And this is from the NCDC NOAA website. So it's thousands. So it says 180,000 weather stations. 2,000 of them are automated surface observation systems in airports, but around 5,000 of them really work at hourly time scales. But the map on the right shows the coverage of the eddy covariance stations in all the Americas, including South America. There are actually 525 of those up to date. So it's pretty ambitious, but if we try to go from these 500 to 5,000, it would mean an incredible amount of data to at least have some estimations of energy budget, soil moisture, and evapotranspiration in these areas. Not trying to replace these towers, but actually getting at least some estimation, some ballpark data in areas where this information is totally unavailable. So we went ahead and tried our hypothesis in Oklahoma, two of those eddy covariance towers, and two of those to validate our results or our inquiries. So here are the four towers that we used. Um, Here's the fetch, or the fetch is the source area for micrometeorological purposes. The weather forcing that we used was measured at the same towers by rain gauges, but we did use a lot of satellite images. MODIS images were used to fit our hydrologic model, specifically leaf area index, NDVI, and albedo. So the model was calibrated using these MODIS images, and the outputs were simulated for all of these variables in the bottom. And here's what we obtained: observations on the horizontal axis, simulations in the vertical axis. So basically, we successfully, oh, my timer. Okay, I'm gonna wrap up in a minute. Um, Here's what we obtain. Red lines is simulations, black lines is observations. Here is a diurnal cycles of net radiation, evapotranspiration, sensible ground heat flux, and surface temperature were successfully captured at these stations. But one of the keys was the use of satellite information, because satellite could let us know, could tell us the change in vegetation with seasons, which is very important to capture transpiration, for example, in the hydrologic cycle. I'm going to go ahead and jump into quickly this topic in 1 minute. This is the use of another machine learning tool to feature elicitation of the variables controlling evapotranspiration in an area. What we're doing is we're conducting the separation of evapotranspiration by relating non-vegetation and vegetation-related variables to a partial derivative of the change in water volume in a certain amount of time. And we are validating our results with eddy covariance towers. So in the end, we separate evapotranspiration into both components. This is part of a paper we're preparing to Water Resources Research. But we basically observed very satisfactorily predictions of ET by only using data from a tower. And we could see the contribution of gross ecosystem production is very high to the prediction of evapotranspiration. And then we compare our results with sap flow measurements. And this is in Oklahoma. This is actually in Arizona, Santa Rita. The red values, the green values are observations of transpiration by sap flow measurements. The red lines are the simulations of transpiration by our machine learning separation technique. And here is the total evapotranspiration simulated and observed here in brown. I'm pretty excited to get new students here in UTEP working this topic. One of them, Smith Doshi, my new PhD student, is going to be looking into TRIPS modeling of this partitioning, as well as Jorge and Stephanie that are going to be moving into soil moisture and partitioning at the tower level. Here's some results of the partitioning that we're obtaining so far in different ecosystems. And then finally, some final work here in University of Texas. We want to continue to improve our understanding of hydrologic processes through hyper-resolution modeling and observations and remote sensing. But at the same time, we want to integrate intelligent systems to white box computer models so scientists get the right answers for the right reasons. One of them is having this L-band radiometer, which is basically when the out-of-shelf microwave radiometer mounted on top of a E2 quadcopter, not like this, but a quadcopter that they are manufacturing for us in Colorado. This is being tested in Colorado right now, but we wanted to test it here in the desert. But foremost, use these to calibrate and validate our models. So we're very excited to do this with other researchers here in UTEP, involving Craig Tweedy, Margaret, and Hugo Gutierrez and their towers, and also Russell Scott in Arizona. We're going to do a lot of summer campaigning, and we're very excited to do this summer. A lot of people have contributed to this work. It's not only myself, but a lot of postdocs and researchers, and I'm missing my new students here, Stephanie Marquez, Jorge Mayo, and Smith Doshin, some other undergraduates, and some of the fundings that I have received so far come from the Army Research Office, the Great Plains Conservation Cooperative, NOAA, Severe Storms Laboratory, and the USGS through the Climate Science Adaptation Centers. And I think with that, I'm going to open up for questions because I've talked too much now. Thank you very much for your time.
Thank you, Hernan. And we do have some questions. And the first one is from Jorge Corredor.
Well, thank you, Chris. Hernan, my name is Jorge Corredor, and I'm the Distinguished Research Scientist at CESSRST. And well, I'm an oceanographer, so all of this hydrology is new to me. And well, you showed Laura Alvarez there, and Laura gave us a wonderful seminar too, just 2 weeks ago. So I'm learning a lot of hydrology lately. And congratulations. I have no questions, but I have some business to attend to. And the business is that CESSRST business is in showing their numbers. So we need to take a group photo, and Shristi, our communications manager, will be taking that photo, but we need everybody to turn on their video. So if everybody will please turn on their video, and Shristi will be in charge of taking the photo. So Hernan, congratulations. That's a very fine talk. You have a very fine group of researchers. And Shristi, let's have the photo.
Christy, your audio is off.
Oh, it's on. Can you guys hear me now?
Yes.
All right. Okay. 1, 2, 3. One more moment. 1, 2, and 3. All right. Thank you, everyone.
Thank you, Shristi.
Okay.
Chris?
Thank you, Jorge. And we have a question from Miguel Velez Reyes. Miguel, we cannot hear you, so remember to unmute yourself.
Oh, I thought I wrote it on the chat, but anyways, I'll read it. You talk about different model parameterization, so how you choose between them, and in your model, in your identification efforts, are some of these parameterizations more identifiable than others, and do you have any issues with identifiability and the quality of data that you are using?
Miguel, thank you for the question. Are you referring to the slide where I referred to the vegetation activity in MODIS, or what specifically is your, Miguel, you're muted.
I don't recall the specific slide, but in some slides you were talking about models and different parameterizations.
Oh,
So
okay. Okay.
there's a lot of
Yes.
work on hydrology and identifiability,
Yes.
so I was curious about that.
Yes. This is a great question, Miguel. Actually, we just submitted a paper with my student about this parameterization. And this is the bottom line. This is the bottom line. The world is moving towards non-steady or transient hydrologic models. And not only hydrologic models, but ecosystem models. It means that we are not only under steady state conditions, we need to update our parameters. Those parameters in hydrology basically relate to vegetation. Vegetation controls a lot of the runoff, a lot of infiltration, a lot of the transpiration and temperatures of the ground. So as far as we get vegetation correctly, our models begin to get things or the outputs correctly. So your question is very relevant because by using MODIS, and MODIS is not the best of the product of the best satellites we have in terms of spatial resolution, for example, because there are others in terms of better spatial resolution. But only using MODIS, our model improved like significantly, just because we could obtain NDVI, for example, very, very accurately. Normalized different vegetation index. Another one of the indexes we could estimate and had the seasonal variability was leaf area index, LAI. And another one was albedo. So only those three control a lot of the parameters in our vegetation models. For example, NDVI controls the transpiration processes. It lets you know how much water plants are pumping out from the ground all the way to the atmosphere, right? By getting the good information from MODIS, the greening time, we could observe that plants are also producing more transpiration during the day than during the night, for example, and that are more active at the beginning of the monsoon season than at the end of the monsoon season, for example. So this information is very important, and we actually need more work, research in correlating the remote sensing information with vegetation activity so we can get hydrologic models to get accurately what we want to model. This is also in the target of big agencies like NASA. NASA is right now having they're calibrating their land surface models against on-the-ground data. But one of the big problems they got, and this is something I have collaboration with them right now, is the first time they plug in vegetation into their models, they had a big smile, like, oh my God, this is it. We need vegetation. We need remote sensing into our models. So they just showed in AGU last year before the virus. I met with them and they said, this totally changed our models, vegetation activity and use of remote sensing, way more important than other variables. We needed this. Our focus was in precipitation and other variables, but having vegetation track really changed our predictions in a good way. So Miguel, I don't know if I answered your question. It's pretty complex. You could write thesis about this, but I hope I did.
I have, so I'm few students of mine have, so I'm aware of that.
Okay.
Okay, so the way we like to do it here is if you have a question, I'll just call your name and then you can unmute yourself and you can ask your question directly to the speaker. And the next person up is Maher Aldeglawe. So Maher, please unmute yourself and go ahead and ask your question.
Good afternoon. Thank you for the presentation. My question is about the data processing. So you said like in two places you talked about machine learning usage. So what techniques did you use and what the characteristics of the data that make you prefer those techniques?
Yeah, this is a great question, Maher, and this is something I'm learning too, and I want to devote more of my time to start connecting models to machine learning, um, because one of the trends right now is to learn from data first and then infer the physics of the models, and this is the way science has been done since the beginning of the scientific method. Is you get observations and then you induce the equations that determine the behavior of the world from those observations. However, sometimes having more data opens your eyes to things that you didn't account for before. So my goal is to start using data analytics and machine learning oriented to find patterns in data and then see if those patterns were already captured by the equations, or if not, then try to incorporate those patterns into the equation. Regarding your specific question into what machine learning techniques I used a lot of them, starting from random forest to principal component analysis. It's, let's say, the basic ones that we all study. But if evolving into more recent ones, I'm starting to use the entropy metrics and mutual information to determine how different or how similar the two distributions are.
Mhm.
And in that sense of the information theory, I've also used the best subsets analysis. Best subsets is a future elicitation technique that helps you find what predictors contribute the most in the prediction of certain predictant. And it does millions of combinations of regressions between predictors to end up showing you what predictors were more important in those predictions. And then at that point you have to take care, because some of them may be redundant predictors. So you make sure you don't involve redundant predictions in your predictions. So at
That's
that time is where your physics begins to act. So remember, you never let statistics work its way on. You always, as a physicist, you have to stop and say, is this okay? Is this correct? You always use what we have learned before from science and then compare it with the new data mining or machine learning techniques we have right now. That's kind of a message or the approach that I use. Uh, but it's a universe. There's a lot of techniques that have been developed by the day in machine learning that I'm eager to learn.
okay.
Okay, next question comes from Tarendra Lakhankar.
Hey, hi, thank you, Chris. Hernan, a very good presentation, and you covered a variety of topics. And we really interested in one of the work you're doing on the L-band radiometer. And one of my student, Carlos Suaha, are you here? I think he was here. He just left. He's working on a similar developing a L-band radiometer that can be used on the quadcopter. So when I see your slides, I said, okay, let's talk. So maybe
it is, yeah.
Yeah, so maybe we'll connect you offline, Chris, if you can share his email address to us. This can be a good, collaboration in future with the Chris.
You want me to just type his email address in the chat box here?
Yeah, sure.
Okay.
Tarendra, please do contact me. Yes, I am very interested in hearing from you and hearing from your student. We could, in fact, do something together. Yes.
Wonderful. And then we also have L-band radiometer, basically on the ground-based. Right now, station at the NASA field campaign in upstate New York. So we're doing some kind of vegetation canopy monitoring using L-band radiometer. So that's another area.
What place are you working in right now? What place?
Oh, New York City.
New York. Okay.
Yeah, City College of New York.
That's great. Let's talk. Yes.
Yeah, sure. Thanks.
Okay. So we're at 1:40 now, and I'm sure people have to go, but there's no reason why people can't stick around and Hernan, are you available to stay around a little more and answer questions?
I am
Okay,
here. Yeah, I still have my coffee.
Okay. I'm happy to facilitate that. We have another question here from Gabriel Rios.
Yeah, thanks, Dr. Collmore. Dr. Moreno, thank you for the presentation. It was very informative. So I have a couple of questions about the virtual weather station that you described that you and your student are working on. The reason I'm interested is because over here, we're currently working on something similar, but using GO16 data to do something at probably a lower resolution. But with regards to the machine learning approach and developing the model, so does the virtual weather station model continually recalibrate with new data that's recorded at the AWA stations? How does that work?
Yeah, that is actually, Gabriel, this is a great question. This is actually the beauty of the virtual towers we are developing, which is actually a model, basically, a real-time model. But the beauty of that is that the model is not static. The model, like the question from Miguel, the model learns from the vegetation images taken by MODIS, basically, which is the one that we have access, is free access, and so everybody can access that. And so the model learns from that image, runs some equations that are based on those images. For example, interception, canopy, maximum interception of water is one that depends on LAI and NDVI. Another one that it's important is the energy that goes all the way from the canopy and hits the ground. There is a parameter that is called the light extinction coefficient that depends on leaf area index. It's exponential with the leaf area index and the vegetation height. And those are only two examples. There are more parameters that we have equations that relate to MODIS that we can use to then get better predictions. And the beauty of that, the beauty of the model is that they're now not static, they're moving, they're evolving, they're learning from satellites. If there is a fire, it catches the fire and then it changes the parameter of the watershed, right? So it's now, there's no vegetation, there's more evaporation than transpiration. In other words, you don't need to recalibrate the models anymore in this sense. The models recalibrate themselves because they're based on physics, and the physics is based on satellite as much as we can capture the physics with the resolution, spectral, spatial, and temporal resolution of those satellites. But of course, with the advance of science and technology, when we get better images, the models will also get better, hopefully.
And then, sorry, Dr. Collmore, just to pile on a second quick question. So I know that the AWA stations, there's a very high resolution since there are 5,000 in the US, but, there's still plenty of areas, especially out west, where there's space between the stations. Mm-hmm. So has any work been done on, interpolating results or maybe running models in areas where you don't have that, that data to feed in like you do at a typical weather station?
Of course, Gabriel. And remember that the objectives of our research were to transform a regular weather station into an eddy covariance station. I mean, into a super station, if you want to call it like that way. So yes, there have been interpolation techniques and models being run. Mostly of them are successful. Most of them are not successful, basically because they need to basically evolve with vegetation. And so the unsuccessful part is because they don't account for renovation. They don't renovate themselves. But the interpolation statistics and models like the NASA land surface model are successful in capturing those fluxes in some areas because they're now introducing vegetation. Keep in mind that the NASA's models are sometimes, the smallest pixels they can model is 1 kilometer by 1 kilometer. So still is large course for, let's say, making decisions about energy balance in a small watershed, or knowing at the scale of the footprint of an eddy covariance tower, how much is sensible heat flux versus latent heat flux. or so on and so forth. So our model is more targeted to footprint simulations rather than core scales, NASA pixel scale simulations. But yes, a lot of people is doing research in this area, and this is something that we're happy to see that's happening.
Great, thank you.
Thank you, Gabriel.
Okay, I just want to, I just put Hernan's email address on the chat room. Can someone just tell me if it shows up? Can you see it? Okay, I see Gabriel nodding his head. Okay, good. So one more question here from Julio. Wait a minute, Julio Ceniceros.
Close enough, yes, Ceniceros, thank you. Hello, Dr. Moreno. Thank you for the presentation. I'm a PhD student here at UTEP also, and so I work with Dr. Craig Tweedy in his lab. And so we go up into the Arctic, the north coast of Alaska.
Nice.
And so I have two, welcome to UTEP. We're lucky to have you. I had kind of two quick technical questions. I'm going to be going up there and I'm going to be adding some sensors to a moving boat, a vessel, that we're going to be taking validation measurements. And so some of that includes weather station sensors and radiometers. So looking at radiation and energy. Since I'm going to be in a moving vessel, I'm going to be, of course, looking at latitude and longitude to calculate zenith angle. But any advice on, having these sensors on a moving platform, like any parameters that I have to be aware of, any advice for that?
This is a great question, Julio, and congratulations on the Arctic field trip. It's going to be exciting.
It's great, yeah.
So so in that area of moving vessels or stuff, I think I'm not the most expert person. Probably Laura Alvarez will be one of the person to contact in the future, so she can give you a little bit more advices, or probably Miguel Velez Reyes could also be helpful in that regard. But it depends, basically, from my point of view, what type of sensors or instruments you're going to have in your vessel. I would say definitely RTK GPS is one must thing you need to have. But however, I know in some areas you're not going to have GPS coverage. So maybe you need a way to geometrically create a network of sensors that allow to know your localization, your position in the North Pole, at least locally, referent to some benchmark places. So
Right.
I know that SLAM is one of those techniques being used by people in machine learning to be able to localize, to know your location without GPS signal. So make sure perhaps you could do some research on how to do this, so that you don't depend on GPS. And this is something that the Army, for example, is looking into, be able to navigate without GPS. Because they don't have access, because they don't want to share their location, or for some different reasons. So definitely do some research on SLAM and ways to geolocate yourself without GPS coverage before you go
Perfect
there.
Yeah, and we'll have DGPSs and like 3 other GPS systems. So yeah, but SLAM is SLAM?
SLAM, yeah.
LAM. Okay, perfect. And then just a really quick other technical question. Your graphs were really great in that post-fire hydrology section. I was wondering, like, you had that precipitation on the top and then like the burn and the runoff. Did you use R to create those?
No, I do use R, the programming language.
Okay.
That's pretty much what I've learned from my PhD, and I stick with it.
Perfect.
But R allows you to create that. I imagine MATLAB or Python also allows to create these type of plots. Yeah, nowadays it's pretty with the new tools.
No, yeah, R is definitely the way to go, I think. So, but yeah, okay, thank you for that.
All right, Julio.
Okay, so I guess that's it. We've had some good questions there, and that was a great talk. Hernan, thank you once again, and we hope to hear from you in the future.
All right, Chris, thank you very much. I hope you guys are all safe and doing great.
Okay. Bye now.
All right, goodbye.